Okay, so recall the definition of Sobolev spaces. HSRN equal to EF in S prime R. Okay, this was the dual space of Schwarz space, and we define, if you remember, lambda, capital lambda S, if psi equal to 1 plus psi squared, square has to be inside, S 1/2 everything, F transform psi, and all this has to be in L2 Rn. Okay, and we had the norm that was, we defined it as S2 equal to lambda SF2. Okay, so it will be 1 plus psi squared S2 F transform norm 2. A special case in which S is equal to 1/2, we will have the F in S prime R such that we have lambda 1/2 F psi. This will be equal to 1 plus psi squared 1/4 F transform is in L2. Okay, we will have a norm of, let's say, H1/2. We will equal to the integral in, let's say, Rn of, okay, 1 plus psi squared. In this case it will be 1/2. Okay, you can put absolute value here and absolute value here. Square d psi. So H1/2 is important for relativistic systems in which one considers the three-dimensional kinetic energy operators of the form, say, p squared plus m squared, and we call that the physics notation p squared. This will be minus Laplacian. M will be just a constant. Okay, the operator minus Laplacian plus m squared is defined by its symbol psi squared plus m squared in the Fourier space. Okay, it will be a Safety operator, and we will consider it for the following initial value problem. IDTU square root minus Laplacian plus m squared u plus lambda e minus mu x, also value of x, convolution u squared u, and here we will have u0x, u0 x, u0t, and R3 C. Okay, this is called relativistic Schroedinger equation or Boson Stars equation with a Coulombian potential. Okay, when you can have any other potential, we're considering this one. One can prove its local existence of solutions. So let m greater than 0 lambda r and mu greater or equal than 0. Okay, and this is mu. And okay, so the initial value problem is locally well posed. Okay, in h1 half r3, and this means that for every unit in h1 half r3 there exists a unique solution um, u in, let's say it's 0 0 t h1 half r3 intersection u in c1 0 t h minus 1 half r3. Okay, and it depends continuously on u naught. Okay, we will have what we said always, this continuous, and well, we have t as the maximal time of existence, and we have either t is equal to infinity or t is less than infinity, but the limit of the norm ut h1 half is infinity. So either we have the t is equal to infinity given global existence, or we have the t is less than infinity and limit when t goes to t, the norm ut h1 half, we have this is infinity. Okay, and this is what we've seen with the regular Schrodinger equation, that we have this granted if this is a self-determined operator, which it is, and we need to prove that this is Lipschitz. Okay, so we have that u naught is in h1 half. Okay, and let's call a minus Laplacian m squared, and if we can say that this is a potential lambda e minus mu x over x u squared u. Okay, and we consider the integral equation as we always did, e minus ta u naught. Okay, and minus I 0 t e minus I t, let's say tau a if u t, or u tau, it has to be tau, and d tau. Okay, so this is the integral equation of the Boson Stars equation. Okay, and here ut is in the Banach space. Let's call yt. Yt is in C0, 0t, h1 half r third. Okay, with some t positive, and the norm u yt supreme t 0t ut h1f. Okay, so we'll see the proof. This is the proof by Lenzman. Okay, and we will have to estimate the nonlinearity through this Lifshitz. Okay, so the first lemma says that for mu greater or equal than 0, the map Ju e minus mu x x u squared u is locally Lifshitz continuous from h1 half or 3 to itself with Ju minus Jb h1 half is less than equal within a constant to u squared h1 1/2 plus b squared h1 1/2 multiplied by norm u minus b h1 1/2. Okay, this is for all u comma b h1 1/2 r3. Okay, so some remarks. We for s in R we introduce ds as mu squared minus Laplacian s over 2, and note that due to the equivalence u norm 2 plus d1 half u less than equal within a constant to the norm h1 1/2, and the same will be in the other side. Okay, because we know the definition of this norm. Then we will just have to estimate the quantities. First, Ju minus Jb 2, which will represent this, and then d1 1/2 Ju minus Jb norm 2. Okay, so in the next video we will continue with the proof of the lemma 1. Okay.